So this video is going to show us how we can find a current using mesh analysis. Alright, so here's a circuit. Notice that we actually have two voltage sources here. And we have several resistors and a capacitor. So remember, the impedance of the capacitor is actually going to be a minus J 20, and we have current, so they're asking for the current through I5, which is also going to be the current through the capacitor. And so we want to find this, and probably the easiest way to do this would be mesh analysis. So with mesh analysis, what we're doing is we're using KVL, Kirchhoff's voltage law, and we're going to sum the voltage drops around a loop. Okay, so the first thing we have to do is define a loop, okay, or all of the loops. And so here is the first loop, and I like to use loop A instead of ones because we have R1 and R2 and R3. So I like to label these loop currents with letters just to keep them separate from the elements. So when we talk about like a loop current, it'll be IA or IB or IC. Which will distinguish it from the current through a resistor or other element here. So I have three loops, A, B, and C. Now, it so happens that the current through the resistor R5, which is the current they've defined as I5, is actually equal to IC. So I5 and IC are going to be equal. However, if we looked at the current through this resistor R2, the current through the resistor R2 is actually the current IA. Okay, so that would be the current I2. Okay, so the current I2 would be the current through the resistor R2, which I'm going to define as going down. And so that's going to be IA, which is also defined as going down through R2, minus IB. Okay, so so that's why I like to use A's and B's for my loops to keep them separate. All right, so officially what we're going to do is we're going to go around each loop. Now there's one loop that I haven't actually gone around, or actually you could probably define a couple of loops. So you could define going all the way around the outside as a loop. Or you could define going through this part a loop. And so there's other loops that you could theoretically do. But what you want to do is you just want to use each little, you actually just kind of want to define each pane. If you think of this as a window with window panes, you want to do each internal window pane. And so that'll keep you from getting messed up. If you try to use one of those other loops, technically it'll work if you're careful and you never duplicate anything. The results would actually still come out okay. However, it's very easy to get confused. What I'm going to show you is how you can do mesh analysis pretty much without even thinking about it. Okay? And so the first thing that you want to do is you want to find your impedance matrix. Okay, so we're going to find the impedance matrix. And then we're going to find our voltage matrix, which is actually a vector, voltage vector, okay, because it's only going to be a column vector. And so what we're going to do is we're going to set up a matrix Z, which is our impedance. and we're going to multiply that times our currents, which we don't know. So what we have to do is find our currents. So we don't know those. All right, now remember, these are all phasors because they're going to have phase angles because of the impedances in there and because of any angles that may be associated with our voltages. All right, and so this here equation, technically, right, is Ohm's law. All right, but the difference is that these are actually going to be matrices, and we're going to be solving for all the currents simultaneously. So the first thing we have to do, again, is build up our impedance matrix. I've got 3 loops, A, B, and C. So that's going to give me my impedance matrix. Z is going to be a 3 by 3 matrix. And so we're going to have this. I'm not quite sure if I can fit it all on here. I may have to slide up the screen a little bit, but I'll try to squeeze it on here. So what we have here is loop A. So if we kind of label this, if we separate this into 3 columns and into 3 rows, all right, so this is going to be row A, row B, or excuse me, column A, column B, column C, and this is going to be row A, row B, and row C. And so what I want to do is for loop A, I'm going to go through and I'm going to add up all the impedances. So all the impedances are going to add up, and I'm going to add them in here. So I'm going to have a 12 ohm plus a 20 ohm. So 12 plus 20. 12 plus 20 is just going to give me 32. Okay. And then I'm going to go to the B matrix and I'm going to add up all the impedances. Now at this point I'm ignoring any voltage sources. And by the way, when you're doing mesh analysis, if you have any voltage source or current sources, you need to convert them to voltage sources. Okay, so you need to do a current to voltage source conversion before you start this if you have current sources. All right, so now we're going to have this one. We have R2 and R3. Okay, so that's R2. I should have wrote that over on the other one. R2 plus R3, which is going to be 12 plus 20, which is also 32. Okay, so this was R1 plus R2 up here. And then for the C matrix, I'm going to have the 12 minus J20. So that's going to be R5 minus J x of C. All right, and so that's going to be 12 minus J20. All right, so there is my column. So in your column, or your my diagonal, sorry, there is the diagonal of my matrix. So what you're looking for is A and A, right, and B and B, and C and C, and all you have to do is just look through that loop and add all the impedances. Look through the loop for each one of those and add all the impedances. So again, we just had resistors in loops A and B, but in loop C we had a resistor and a reactance. So we have to make sure we keep track of J's, but you just add those up. It's so easy. And so now what we want to do is we're going to come over and start back at loop A. So we're over here. Okay, so over here you have A and B. So what we're looking for is all the impedances where A and B are together. And they're opposing each other in this case, right? Because A is defined, we defined A as going clockwise, which means it's going down through R2. And we defined B as being clockwise, which means it's going up through resistor R2. And so therefore, what we have to do is we add those together, right? But we're, well, we add together all the reactances and impedance, all the impedances in here where both A and B are shared. Okay, so R3 is not shared. IA does not touch R3, so we don't include R3. And so we're only taking the ones that are shared, and we're going to subtract those off. So I'm going to subtract off 20. Okay, so I'm subtracting off 20 because of R2. Now, if we look between IB and IC, they share a voltage supply, but they don't share an impedance. There's no resistors or capacitors or inductors in here. There's just the voltage supply. All right, so they don't, excuse me, A and B, they don't even touch. A and B do not even touch. So that's just simply a 0. All right, and now we already did A and B here. So all we have to do is copy this down. It's always going to be symmetric. So if it was minus 20 up here, it's minus 20 there. Same way with this one down here. We just copy it. Okay? And so now the only one we have to worry about is where B and C are touching. So this is the case where we have B. What is B touching and C touching? All right, and again, that I kind of already said that. The answer is B and C do not have any impedances touching. They do share the supply voltage, but they do not share any impedances. And this is the impedance matrix, so those are simply 0. All right, so that is my impedance matrix. All right, and that's multiplied times the currents. And so that's going to be the current IA and the current IB and the current IC. Okay, which we don't know. That's what we're trying to find out. And now we got to build up our voltage matrices. So now we're going to build up our voltage matrices, which again, it's actually just a column vector. Okay, so a vector is a matrix that only has either one column or one row. Okay, so now what we have to do is we go through for loop A, because remember this is like A, B, and C here. And so we're going to look, and the current is going up through. The current is going up through this source. Okay, so IA being the current, because this is row A. So we're doing row A, and row A is going up through this first source. So that's going to be a positive, and the positive sign is up here. Okay, if the negative sign was here and the positive sign was here, we would have to put a negative. Okay, or if the current was going down against the negative, we would, or against the positive sign, we would have to do that. But so this is just going to be 100 angle 0. And then if we look at loop B, okay, loop B, again, loop B now is going down against the supply, okay, because the supply is positive at the top, so it's trying to push current up, okay, using a conventional current flow, it's trying to push current up, but B is defined as going in the opposite direction, so that's going to be a negative 200 angle 20, but then C is going in the direction that this voltage source is going. So that's going to be a plus 200 angle 20. Okay. So now notice this, this negative sign that negates the entire voltage source, including the angle. Okay, so it's minus 200 times that, which basically a minus sign is 180-degree phase shift. When we're talking about AC, the negative sign means that we have 180-degree phase shift of the sine wave. All right, so that is our matrix so that we can now solve this matrix. So if we come over, I really prefer to use Octave to solve this. Okay, so if we come over here, we can create our impedance matrix Z, and I'm just going to use a lowercase for typing here. Remember, Octave is case sensitive. And we need to just put this row in. So we're going to have a 32 minus 20, 0, comma, minus 20, 0. And you could do this one of two ways. You could do it all on the same line by putting a semicolon here, or you can actually just hit the enter key and go to the next line, whichever you prefer. But we're going to have 20 minus 32 and 0, which is going to be the middle row, the B row. And the C row is going to be 0, comma, 0, comma, and then a 12 minus J times, don't forget the times there, times 20. And so this now is my impedance matrix. So there is my impedance matrix. Okay, and notice because I have a J term in there, and actually it uses the mathematical term I in the software here, but it puts the I on all the values and just says plus 0I for all these that are pure resistance. All right, but it goes through and displays it. So this is my matrix for my impedance, and now I need to put in my voltages. Okay, and so with the voltages, again, I'm going to use lowercase v just for ease of typing, 100 angle 0. So since it's angle 0, I can just ignore that. Now this is a column vector, so I need to hit enter or use a semicolon there to go to the next row. And then I'm going to put in a minus 200, and now I've got an angle of 20. So this does have a non-zero angle, so I have to apply that. So I'm going to do exp, which is e to the I, okay, and it's going to be a plus j times 20 degrees. However, when you use this, so and when you're doing a TI-84 calculator also, you have to be careful here because it, even though your calculator may be set to degrees, this mathematical expression only works with radians. So we have to have 20 degrees, but now we have to convert degrees into radians. So I'm going to multiply times pi radians divided by 180 degrees. So we have 20 degrees and we have 180 degrees, so the degrees cancel, and I'm going to be left with the radians, which is what this equation needs. And then I'm going to have to do the exact same thing here, but I don't have the negative sign, right? So down here in this lower section, there's no negative sign there. All right, and then I'm going to close my bracket. Okay, so you notice like I put this negative sign around this whole thing. So I used parentheses there. Here I didn't have a negative sign, so I really don't need that parentheses there. Okay, it doesn't hurt if you put it there, that's fine, but if you're going to put it there, you better make sure you put the closing one on the other side. Okay, either way will be perfectly fine. Now when I hit enter, this gives me my voltage column vector. All right, and you can see the values are actually all given in rectangular form because that's the way the Octave software displays it by default, is just in column form there, or in rectangular form. All right, but see, now I can calculate my current. So I can say I now, and what we're doing when we solve for I, okay, so if we come back over here, you know, basically what we have to do is we're going to be solving for Ohm's law, right? This right here was Ohm's law, so if we rearrange it, because we're solving for I, that's what we don't know. So when we solve for this, then we're going to say that I is equal to the voltage divided by the impedance. Now, but this is a matrix that you're trying to divide, okay? So this is a matrix that you're trying to divide here. And so matrix math is a little more complicated. So, but the Octave software has a lovely feature in here called the backslash division sign. And it'll do the correct math for us. So what we want to do is we're going to put in here Z backslash V. So you notice how if you kind of imagine this backslash, if the V was to slide up a little bit, it would kind of be on top of the Z. Okay. So when I divide this, then I'm going to have I is equal to, and then we're going to have our Z matrix, our impedance matrix, divided by, or backslash, the voltage matrix. So again, this, if you can kind of imagine that, let me write it over here, like, okay, so we have this Z, V, so, if you kind of slide V up here, it's more on top. Okay, so that's what this is doing. It needs to be a backslash, not a forward slash. Okay, if you try to put a forward slash here, okay, you're going to get some weird error about non-conformant, and that's because you're not actually doing proper matrix math. It has to be this backslash V. Oh, finger on the wrong key there. And so when you get this, notice that your I now is going to be a column vector, right? Just like we showed over here, right? Over here we have IA, IB, IC right on top of each other. So when you do this math, that's what you're going to have. You're going to have IA and IB and IC. Now, of course, this is actually showing in rectangular form because that's the default setting for the Octave software. It always just stores the values in rectangular form. All right, so whether it's rectangular or polar, it's the exact same value. It's just how you're displaying it. So if we want to display, now really remember what we were looking for over here was the voltage, or not the voltage, excuse me, but the current I5. So we were looking for the current I5. And so the current I5, though, I already said that on this slide, was equal to IC. Okay, and so this is IC. So there is my current. However, anytime we're going to display the current, we always want to display the current in polar format. So I'm going to call this like I5 polar. Okay, and I'm going to use the absolute value function built into the software here to basically apply Pythagorean's theorem and calculate the magnitude of the phasor. And so, but I just want the third value. Okay, so here's my first value. Remember, it's a rectangular, so it has a real and imaginary part. All right, but what I'm looking for is the third value, the bottom one. So I'm going to say I3 to just get that third value. And then I'm make sure you close all your parentheses, and then I'm going to use the angle function to calculate the angle. Now again, the angle is calculated in radians. Okay, so I need to multiply it times degrees. So this time I'm going to multiply times 180 degrees and divide by pi radians. So the radians cancel out and I'm left with degrees. And so there is my answer. So my answer is 8.5749 amperes at 79.0362 degrees. And so if I'm going to put this into Blackboard, right, I would type in 8.57. Okay, there's a 4 to the right of the 7, so we don't round up. I'm going to put a space amperes, put in my angle sign, and then it's going to be 79.0 degrees. And I can't do an actual degree symbol in here, so I'm just going to type that in. But this is how I would type that into Blackboard. Okay. So I want 3 digits. So there needs to be 3 digits for the current magnitude and 3 digits for the angle of the current. All right, so there we've used mesh analysis to solve this series parallel circuit with actually 2 voltage supplies and come up with the solution.